Hello there, Physics 30. Welcome to EMR Ch13 Lesson 2. Alright, so last lesson we just finished off with basically the different types of light. It was quite a long lesson, but it's pretty interesting stuff, at least in my mind. Alright, so now we're going to get to lesson 2 here, and the first thing is that we talked about the different types of light, but there's something that we had to figure out first. Is what is the speed of light? So this lesson is all about the speed of light, how we find it and stuff like that. So we know that the speed of light now is approximately 3 times 10 to the 8 meters per second, right? Which is 300,000 kilometers per second. It's very fast, right? And so the two things we need, if we want to calculate speed, what do we need? Well, we need a distance and a time. So somehow we had to have a distance, which was easy to measure, right? Anyone can measure distances, but we also needed time. And the issue with the time is that they were super small numbers, right? So you think about it, 300,000 kilometers, you can't see that far because of the curvature of the Earth, right? I think you can only see something like 8 kilometers. I can't remember the exact number is, but in order to calculate the speed of light, we need a distance and a time, all right? So the first clever thing that everyone did was they said, well, what if we double the time? So instead of just measuring the distance from one spot to another, we would have it come there and back, right? So the first person is to do this is Galileo. So Galileo says, well, I'm going to go to the top of the mountain over here, and I'm going to send someone over to this top of this mountain, right? And so Galileo says, all right, well, I'm going to stand here, and I'm going to have a lantern. Okay, I'm going to stand with my lantern. You stand over here with your lantern. And these mountains are about 2 kilometers apart. 2 kilometers apart. And so when he turned on his lantern, right, and so Galileo thought he was being clever, right? So he turned on his lantern, and the light travels all the way here. And then when this person sees it, he's like, oh, I see it. Right? If this person sees it, then he says, he turns on his lantern and it comes all the way back, right? And so the total distance is 4 kilometers. The total distance is 4 kilometers. The problem is that Galileo was trying to measure this using his pulse, right? Using his pulse. And the time that it went this distance was 0.0000666 seconds. So you can't exactly measure that using your pulse. It doesn't quite work, right? And so that was a big issue, right? So the 4 kilometers wasn't far enough, and it was too small. So the timing device, you couldn't time using that, all right? So then the next person was a little more clever, right? All right, so the next person was more clever, and this was Romer. I don't even know the people's names. So Romer measured basically the amount of time that it takes for the eclipse between the moon on Jupiter and Jupiter, depending on the position of the Earth around the sun, right? So he talked about the sun, he's watching things, and so what he actually did is he basically used geometry and the eclipse of the sun, and he originally measured it to be 22 minutes. I know the slide said 16, but he originally measured there to be 22 minutes, right? Then he figured the difference between, he figured it takes 16 extra minutes, and he knows the difference between the sides. So he figures out that when Earth's on one side versus the other side of the sun, right, that the difference there was 22 minutes. And since we know how long it takes for it to go around, we build on Einstein's equations, all that stuff, right? He said that it was 2 times 10 to the 25 meters times 10 to the 8, not 2 times 10 to the 25, 2.25 times 10 to the 8 meters per second. Okay, and this was in 1676, so he's doing pretty good. Obviously, everyone around there was like, that is ridiculous. You're wrong, right? Like, just not a chance. Okay, and the crazy thing is that it does seem ridiculous, right? And at this time, they've kind of measured the speed of sound to be about 343 meters per second, right? Okay, that's 3 times 10 to the 2. Okay, they're not expecting it to be 1,000,000 times larger. They'd say, well, 10 times larger, 1,000 times larger, maybe, but you basically Raman are saying it's 1,000,000 times larger. And so they're saying, that's ridiculous. Your math is wrong. So, and this is very similar to, the idea of we're trying to prove something new. And so it's very hard to do. All right. So the first attempt was measure the speed of light came from Fizeau. Okay. So Fizeau had a apparatus, right? And basically what he did is he sent light and it would go down and through. And so he used about 8.6 kilometers was his thing. So when it down and back, it was 17.2 kilometers in total. So he had a little more time, right? But he made this rotating wheel with notches in it, right? Okay. And so what he did is he rotated that wheel, all right, and he changed the speed of that wheel rotating. And basically the time to go from notch 1 to notch 2, because that's when he would see the light, right, is basically the time it would take for it to go down and back. Any other beam would either get stopped here or stopped on the way back, right? So it's how much time it took. So he basically was splitting the light into pieces, all right? And basically what that does is this rotation, how it rotates, is a timing device. Okay, it's a timing device, right? So basically what happened is by rotating that notch, right, on the wheel, you'd have notch 1, and then you'd have notch 2 and notch 3, right? Is the light would pass through the first one, hit a mirror way away, and then when it came back, this notch would rotate into its spot, and it would come back through that notch again, and then he would see it, right? He'd see with his eyeball. Look at that, pretty eye, right? So he'd see with his eye. So between the notches, and then he knew that how much time it took to go from this notch to this notch, right? The time it took for notch 2 to move into notch 1's position is the time it took for it to go the 8.6 kilometers and back, right? So he came out with a speed of 3.13 times 10 to the 8, 3.3, which is really good. Like he actually is a little bit fast, right? He's a little bit fast, but he knew this, okay? But 3.3 again, times 10 to the 8. So now we've got two people who've came with numbers that are in the times 10 to the 8 era. And so that's like, holy man. So now people are starting to realize this is realistic. And so we have another person who came up with a very similar system, all right? This is Michelson experiment. So this is the experiment that you need to actually know, right? Okay, this is the experiment you have to actually understand. All right, and so what Michelson did is he basically put an 8-sided mirror, all right? Put an 8-sided mirror. And he put this 8-sided mirror, and what it would do is basically when the light hit and went down and came back, the rotating mirror, right? The rotating mirror would have to rotate exactly 1/8. All right. If it rotated exactly 1/8, then you would get this idea. So the source comes in, goes down and back. This is a large distance. Okay, this is a very large distance, right? We're talking about multiple kilometers. All right, and it came in, right? And so what you do is you change the speed of the rotating mirror, right? If the mirror is rotating too fast, then your light will do this, go down, and then bounce off this way or bounce off this way. It won't go straight to the observer, right? And so it has to be rotating the exact right speed. Once you get it at the right speed, then the observer would see a burst of light, then a burst of light, then a burst of light, then a burst of light, because we'd have one hit, come down, go hit him in the eye. Then you have another one hit, come down, go down, hit him in the eye, right? And so the observer, if this is rotating too slow or too fast, right, this is rotating too slow or too fast, wouldn't see any light. But once you got the right speed, then you would, right? Now you could actually get it going too fast, all right. But he basically came out with a very close to 3 times 10 to the 8. All right. I think the actual number is like 2.97 times 10 to the 8, but we just use 3 times 10 to the 8 in physics 20 and 30. All right. So if you're asked a question about the frequency of rotation, all right, frequency of rotation, right? That's just frequency. It's hertz, okay, or the experimental speed of light. Okay, if you're asked for the frequency of rotation, you're going to use the 3 times 10 to the 8. But if you're asked experimental speed of light, you can't use that. All right, you can't use 3 times 10 to the 8. It's asking you to calculate it, right? So Michelson performed this experiment on the top of Mount Wilson, where he reflected the light off a spinning 8-sided mirror a distance of 35,200 meters to a stationary mirror and back. What is the minimum rotation speed of the spinning mirror in RPS? Okay, RPS. RPS should mean something to you, right? RPS, well, that is hertz, right? 1 hertz. All right, so we're talking about rotations per second. That is the hertz, okay? So we're going to have this, and what I went through is I did the distance. The distance is 70,400, okay? We can ignore this distance, okay, from this distance here, because this is just showing, like I know you'd have to do trig and stuff, but this is just showing it in a convenient way so we can actually see it. That distance is actually negligible. So we're just going to say it's a linear distance, so straight out and straight back, of 35,000. So he's talking 70 kilometers. So he does this, and we find that light will travel, that's 70 kilometers, okay, in 2.346 times 10 to the negative 4 seconds. All right. Now, that is it for it to rotate. This is 1/8 rotation, right? It only has to rotate. This is 1/8. 1/8 rotation. So I'm going to take that number, I'm going to times it by 8 to give me, it will have a full rotation. It'll take 0.000187733 seconds for one rotation. Okay, so that's my period, right? That's my period, but I want frequency. So I know that frequency is 1 over the period. When I do that math, I'm going to get that the frequency is 532 hertz. Okay, 532 hertz. Be 0.67 if you wanted to do sig digs, right? We don't actually use that 8 as sig dig because it's exact, right? It's exact. So we'd use a 35,200. So it'd be 3. I'll just write that down properly here. So 532.67 hertz, which is our rotations per second. Okay, so again, I'll review what I did here. So I did the distance, right, and the velocity. Okay, it didn't ask me for the velocity. It asked me to figure out the time, right? And so I've got v equals d over t, right? Light doesn't accelerate or slow down. So we have t equals d over v. Divided those. I'm going to double check my number right now. Yeah, 2.346 repeated times 10 to the negative 4. And that's for 1/8 of a turn. Then we're going to times it by 8 because that gives us a full rotation. So it takes that many seconds, 0.0018 for one rotation. And then we're going to turn that into a frequency, right? So we have to get this mirror rotating at exactly 532.67 hertz. If we have it rotating too slow or too fast, the light won't make this path. Okay, it'll just go and bounce off randomly, right? If it's not exactly this, right? If it's too slow or too fast, right? It's either going to reflect wrong there, or it's going to reflect wrong on this side, right? So it has to be exactly 1/8 of a turn. Okay. All right. So that's that. Alrighty. There's another thing that's important here. You can watch these videos. These are purely for interest sake if you're got nothing else to do. This video basically compares the difference between when you see how fast light is versus when you hear it. All right, please note there is some graphic language. It's not super bad. I've shown it in some classes before, but don't, it's not an important video if you are, not an important video to watch if you're concerned about graphic language. All right, and this is just basically a failed space mission. All right, it was unmanned. You're not watching anyone die. Don't worry about that. Okay, it was just carrying supplies up to the International Space Station, and it went kablooey. All right. Okay, so you can do practice problems 1 to 3. You also can, I know it's on the next page, but you can also do your 8 to 12 in your anticipation guide. All right, have a good day.